So, covering our last section in this chapter, which is the second fundamental theorem of calculus. And the second fundamental theorem of calculus is, well, do you remember what the first fundamental theorem of calculus was?
Is it differentiating integrals, or is it integrating derivatives?
Integrating a derivative gives you back your original function. If we do the integral from a to b of f prime of x, that's equal to f of b minus f of a. This is exactly what it was, but notice that if we integrate the derivative of big F, we get a functions in terms of big F. Right? Similarly, ultimately this section's coming down to this proof right here, that if we differentiate with respect to x, this thing, we get back the inside function. Make sense? So it's just the counterpart to this thing. That's what this section's practically about. We'll work up to proving that, and then there's a couple corollaries that just help get you comfortable with it. So let's jump into it. First thing we're going to prove is it's called the mean value theorem for integrals, and it's because it looks a lot like the mean value theorem. Maybe we'll really quick remind ourselves of the mean value theorem. What did the mean value theorem tell us? So we'll say if you had a continuous function, so we've got some continuous function on some interval, we'll say AB, doesn't matter what the interval is. It said that if your function, if you have f of a is less than or equal, well, we'll say strictly less than f of b, then there has to be some point in between them, some point x naught, such that the value at x naught is between those two values. So if a function attains two values and it's continuous, then the intermediate value theorem gave us that it achieves every value in between those 2 points. Oh, that's intermediate value theorem, sorry. Mean value theorem was the average one.
Yeah.
Sorry. We will be using the intermediate value theorem today, which is why that came to mind. I think we will. Sorry. Mean value theorem was, okay, continuous function, same thing. Let's have it increase from a to b. So here's a tie to b, here's a tie to a. Mean value theorem was that the average change of the function between these 2 points, whatever that is. What is the average change from here to here? That's the change in height over the change in x. Rise over run. That's the average slope of this function from this point to this point. And if we were to plot what that looks like, it looks like that, aligned with that slope. That's the average change. What the mean value theorem said is that if this is the average change of your function on that interval, then somewhere in that interval there has to be a point, x naught, such that the slope of the function at x naught is exactly that mean value. So there exists x naught such that f prime of x naught, the slope at x naught, is equal to this thing. Now, that's the way I always write it and think about it. The way that we did this in our book is we actually proved that f of b minus f of a is equal to, oh no, that's what we did, sorry. That's exactly what we did. Okay, so what we're going to be doing is we're going to be proving a similar thing, mean value theorem, with integrals. We're going to prove that, notice that if we move this b minus a to the other side, so let me manipulate this for just a second. I'm going to move the b minus a to the other side, and I think that that's going to help give us intuition for what we're going to do over here. So this is the mean value theorem. This says that at some point f of x naught is going to be equal to, you could have thought about this as b minus a over, and this integral part's going to act a lot like f of b minus f of a over here. Remember that when you integrate f of x, what do you get? you get something that looks like this. So this part right here is going to account for our f of b minus f of a that we're using over there. But what we're essentially going to prove here is that if I have some integral, if I'm doing some integral on this closed bound, so let's say I'm integrating this function now. So if I integrate this function, that gives me the area under the curve right here, right? The mean value theorem of integrals is essentially saying I can find some point x naught such that the height at that point, here's f of x naught, if I were to do just the rectangle with that height, I get the same area.
Oh, okay.
That's what it's essentially saying. So, if you move the b minus a over here, then f of x naught times b minus a is the area of a rectangle. It's f of x naught times b minus a, that would be that rectangle, is equal to the integral from a to b of the function. So you've got the integral of some function, it gives you an area. We're saying that there's some height we could have chosen that when you take the area of that rectangle, you get the same area as the integral. That's intuitively what we're doing. Does that make sense?
Yeah.
That's big picture how we're doing this. Okay. So let's go through the actual proof now. Maybe leave that quick little sketch just in case it helps to reference. Small proof, so maybe we'll be fine. All right. Since f is continuous, then by the extreme value theorem, remember the extreme value theorem? A function attains a max and a min on a closed interval. So since f is continuous, then by the extreme value theorem, there exist 2 points x sub little m and x sub big M such that f of x sub little m is smaller than everything. It's the minimum value the function achieves on the interval. And f of x sub big M is the maximum value the function achieves on the interval. And so everywhere in between, f of x is going to be less than or equal to or greater than or equal to the min and less than or equal to the max. So this is exactly the way that we were using big M and little m in the past. Now we're just referencing its x coordinate instead of just the height. So the value of x sub little m is exactly what we meant by little m in the past. How we've been using that. With me so far? Nothing confusing? Okay. So then, if we do the area where we use the minimum height, so the minimum over here, if we use our picture, f of x sub little m is this height, and f of x sub big M is this height. And so if we do the rectangle where we use the max height, we're going to get more than the area. And if we do the rectangle where we use the minimum height, we're going to get less than the area. That's essentially what we're going to say in this next line. Then the minimum times the distance is going to be less than or equal to the actual area is going to be less than or equal to the max times the distance. With me? Okay, now take this whole string of inequalities and divide them all by b minus a. Remember, b minus a is going to be a positive number because for sure b is bigger than a. So we're dividing by a positive, so our inequality signs stay the same. So when we divide this term by b minus a, we're left with that. When we divide this term by b minus a, we're left with that. When we divide this term by b minus a, we're left with that. With me? Okay. But now, by the mean value theorem, there has to exist some point in AB, not the mean value theorem, the intermediate value theorem, the regular intermediate value theorem. There has to exist some point x naught in AB such that f of x naught is equal to this value. Notice that f goes from x sub little m to x sub big M. Therefore, it achieves every value in between those two values. So somewhere in between, it has to achieve this value. So there has to be some x naught such that f of x naught is equal to that value. That make sense? And I think that's it. Okay, any questions on the first one, or ready to just continue? Just continue? All right, let's look at our next one. Let f from a b to r be integrable, and let big F, typically we use big F to represent the integral of little f somehow. So let big F be a function from AB to R by f of big X is equal to the integral from some number A to X of f of t dt. Okay, so don't get lost in notation here. The reason I'm doing f in terms of t instead of x is that you don't get confused by how this function works. When you plug 2 into this function, that is the integral of this function from a to 2. When you plug in 10 to this function, that's the integral from a to 10 of this function. So x is changing how far we integrate. So if we draw little f sub x over here, here's A, can go all the way to B. Here's little f of x. Big F of, or here's little f of t. We'll think about this in terms of t, so here's our t-axis, just so we don't get confused. X is going to be a value here, and we are integrating from a all the way to x, and big F gives us that value. So big F then, big F of x gives us this area. And as x goes this way, big F of x gives us a bigger area. So that's the value of this function. Notice, if you knew what little f was, and you knew what a was, then for any x I gave you, you can find the number that this is, right? You just plug in x and you can solve it. You understand what I'm saying? Okay, so it's just a function. Don't get confused by the fact that that's a whole lot of notation, and that we have another variable in there that we don't really care about. The author this whole time just uses the integral from a to x of f, because he didn't want to confuse you. But I'm going to put the t dt in there to make sure that you realize this function does not depend on that x value. Only how much area you're calculating depends on the value. Okay. So, restart. Let little f be a function from ab to r, be integrable, and let big F from ab to r be this function, f of x is equal to the integral from a to x of little f. Then big F is continuous. That's what we're proving. We're proving big F is continuous. Okay, so since little f is integrable, then big F is well defined. What do I mean by that? Notice that for any value of x that we can plug in for big F, we're going to get an integral from a to, up to, and possibly including b of little f, and we know little f is integrable from a to b. So this function big F on this interval is well defined. So we're good there. It's at least a well-defined function. And little f is bounded. How do I know that little f is bounded?
That's what you said.
Little f. How do I know little f is bounded?
Because it's a continuous function in a closed interval.
It's continuous on a closed interval. That is enough, I think. Continuous function on a closed bounded interval is bounded. I think that's right. But it's also, we know it's integrable, which means for sure it's bounded, because the integral comes out to an actual number. Can't show off to infinity. But I think you are right. So, and we know that little f is bounded. What does it mean for little f to be bounded? It means that I can find two numbers that little f is always in between. So since little f is bounded, then there exists some positive big number m such that negative m is less than or equal to f of t is less than or equal to big M for all values of t that you can plug into little f. Little f, so if I pick big M to be this number, then little f on this interval is always between m and negative m would be clear down here. Right? We don't need to worry about finding as close of numbers as we can. There just exist some numbers. Doesn't matter how big they are. But there is some number big M such that this is true. We can sandwich it this way. That's all we're saying there. Good up to here? Okay. All right. So next, let U and B be any 2 points in AB. Should I say? Maybe I'll come back and make that note when we're done. So let UV be any 2 points in AB, and we'll call whichever is the smaller of them U. Then, f of v, what is f of v? By definition, notice I dropped off the t notation here because I didn't want to write a bunch of t's, but I think you'll understand what I'm saying. F of v, what is the value of f of v? It's the integral from a to v of f, right? F of t dt. Which is equal to, notice that u is a value between a and v, right? Because u is in the domain, and v is greater than u. So if we calculate the area from a to v, that's the same thing as calculating the area from a to u plus the area from u to v. Splitting the integral into two calculations. And that's actually one of the first things we proved way, way back, is that you can take an integral and split into two, right? Which is equal to f of u plus the integral from u to v. This right here is f of u, and then that's still just that. You with me? Okay, so then the integral from u to v of f is f of v minus f of u. Great. Now since negative m is less than, okay, now here's maybe where I can drive my point home and then we continue. What I'm going to be showing is that as the distance between u and v goes to 0, then the distance between v's goes to 0, and so this function's uniformly continuous and therefore continuous. You remember what uniformly continuous was? If you have two sequences of number, we typically use un and vn, such that in the limit their difference goes to 0, then the limit of their values goes to 0. That's what meant to be uniformly continuous, which was stronger than just continuous. So I'm going to show that as the distance between u and v goes to 0, the distance between f of u and f of v goes to 0, and therefore this function is uniformly continuous and therefore continuous.
So all integral functions are uniform.
If they are on this closed bounded interval. Yep. Okay. So back to here, I think we understand that. And that's why I was getting my f of v and f of u. That's why I was manipulating this to get these to show up. Okay, so now continue. Since negative m is less than or equal to the value of f is less than or equal to big M, f here is sandwiched between big M and negative M, then negative m times the distance is going to be less than or equal to the value of the integral, the area here, is going to be less than or equal to, right here, m times the distance. Notice that big M times the distance would give me this area. Negative m times the distance is going to give me a big negative area. And the integral is going to be somewhere in between. Notice that the integral didn't have to be up here. It could have been some negative integral down here giving us a negative area. So it's not trivial that we're putting this thing over there. Because we couldn't just say that the area is always greater than or equal to 0, for example. Because it could be negative. Good with this so far? Okay. So then, what does that give me? Just simple substitution. I know that this integral is f of v minus f of u. That's the only substitution I make going to here. You with me? Now, notice that I have this sandwiched between the positive version and the negative version of a value. And so it's sandwiched between their absolute value. This right here is the absolute value of those. And if I force this to always be positive, where are we? If I force the area to always be positive, it's still the same. We could have used an absolute value of this the whole time if we wanted. And it's still going to be in that inequality, because that's just forcing our integral, whatever it is, to be positive always. So from here to here. So adding the absolute value to that, that was trivial. It was getting the absolute value over here that we cared about. Good? Okay, so notice now what happens as u and v, what happens as the difference between u and v goes to 0?
The whole side goes to 0.
Yeah, this whole thing goes to 0, so this whole thing goes to 0.
Because it's positive.
Which means uniformly continuous. Right? Notice now that u and v are just 2 points in the domain. As u and v approach, as their difference approaches 0, then the difference between their values approaches 0. Therefore, it's uniformly continuous. And therefore, it's continuous. Is there something weird? Just need to look at for a second. Are we good? Good? All right. So now, let's move to the major theorem of the section, the second fundamental theorem of calculus. So let f from ab to r be a continuous function. Then the derivative of the integral of the function just gives us the value of the function at whatever that x is. That x is what we were integrating to, and it's what we're integrating with respect to. So this is kind of a weird function. We're integrating with respect to the boundary that we're integrating to. Has nothing to do with this internal function. That's just what we're integrating. And notice that f was expressed in terms of t right here, but we have f of x right here. The same x that was up there that we're taking the derivative with respect to. Okay? Don't get lost in the notation. Okay, for all x in AB. So now let's prove this. First thing we're going to do is we're going to define capital F from AB to R by f of x is equal to the integral of little f from a to x. And we're going to let x naught be some point in this interval. Now, let x be any point in there such that maybe help you see what value we're ultimately trying to find. We are trying to show that the derivative with respect to x of the integral from a to x of f of t dt, we're trying to figure out what this thing equals, right? Now we know what the derivative with respect to x of this, we know how to set that up. We know that this is equal to the limit as x approaches x naught of the integral from a to x naught, or a to x, of f of t dt, minus the integral from a to x naught of f of t dt, all over x minus x naught. Right? Just without having any clue how to even begin evaluating this, just plugging in, we know we can plug that in like this. So, what I'm trying to show is that the limit as x approaches x naught makes this whole thing equal to f of x. Or in this case, f of x naught, because we're going to be doing the limit as x approaches x naught. So this is what I'm trying to show, and this is what this is. So in this, I'm going to choose to approach x naught coming from above, and that's arbitrary. We could have also approached it coming from below. So x is just some value bigger than x naught, and we're going to continue from there, but we could have also approached this thing from the bottom if for some reason we can't from the top. You can do one or the other. And it would be the same. It would just change your signs, because now you have to worry about, is f of x minus f of x naught positive or negative, or is x minus x naught positive or negative? So we're just going to make sure that x minus x naught is the positive value. In other words, it just changes signs, but everything else follows the exact same. With me? Okay. So let x be some point in the domain such that it's bigger than x naught. And notice that means that f of x minus f of x naught. Now we defined this function f to give us our integral, so that we don't need to write this notation all over the place. So now this with how we've defined big F is the same thing as a limit as x approaches x naught of f of x minus f of x naught all over x minus x naught with how we've defined big F. So this saying the exact same thing, just writing it in terms of big F. So let x be some value such that it's to the right of x naught. Then f of x minus f of x naught is equal to, I just need to know the order of this so I know the order of my integrals here, is equal to the integral from a to x minus the integral from a to x naught, exactly what we had up here, which is equal to the integral from x naught to x. If I do, maybe draw a picture of that one if for some reason it's not appealing to your intuition. Here's A, here's B, here's our function. We're saying, where were we? Right here. Remember, x is a point to the right of x naught. So x naught somewhere over here, and then x is some point to the right of it. We're saying that the area of the function from a to x, so the area from here to here, minus the area from here to here, so if we get rid of all this area, leaves us this area. That's what that's saying. The integral from a to x minus the integral from a to x naught leaves us the integral from x naught to x. Good? Okay. Okay, so then by the intermediate value theorem, then for each x that you choose, there exists some point, I'm calling it c of x here, to remind you of the fact that this point depends on the value of x. So we have x naught and we have x. For each x that you choose bigger than x naught, there's going to be some point in the middle, we're calling it c of x, such that the value at c of x is equal to 1 over x minus x naught times the integral from x naught to x of f. Notice that this right here is just this, what we started with. There's some point in the middle of those two numbers such that the height at that point, if I calculate the rectangle with that height, I get the same area as this area right here. That's what we're saying. There exists some point, call it c of x naught, c of x, such that the height, no, we were up here, such that the height at that value, notice move this over, times the width, gives you a rectangle whose area is equal to this area. So anytime I see this, I'm always in my mind thinking about it this way. I'm thinking about f of c of x times x minus x naught is equal to the integral from x naught to x of f. Some height times the width that we're talking about gives us a rectangle whose area is equal to the area under the curve. So for each x you pick, there exists some other point, call it c of x, or we could have done c sub x, doesn't matter. Just reminding you that depends on the value of x, such that this is true. Right? So, since c of x is always sandwiched between x naught and x, then in the limit as x approaches x naught, as x gets closer and closer to x naught, c of x has to approach x naught. Because it's between x and x naught. Good? Okay. So finally we're ready to take our limit. So then the derivative of the function, the derivative of the integral, just putting it all together now, so that you can see it all in one go. The derivative of the integral is the same thing as the derivative of f of x. By definition of f of x, this is just like a sum up from the very beginning of what we just talked about. The derivative of the integral to x of some function is equal to the derivative of its integral function is equal to the limit as x approaches x naught of f of x minus f of x naught over x minus x naught is equal to the limit as x approaches x naught of x minus x naught times the integral from x naught to x, which is equal to, finally now, we know what this is. this is equal to f at c of x. So we're going to replace this piece now with f at c of x, and still take its limit, and then in the limit, since c of x approaches x naught, and f is continuous, then f of x, or f of c of x is going to approach f of x naught. And we're done. So this line was just a big summing up of all the steps that we did, so you can see it from start to finish, every piece of logic that we used. So you wrap your head around this line, you get the whole proof. And this is what we started with trying to figure out. We said this is the same thing as this by how we define big F. Then we know exactly what it means to take the derivative of a function. That means this, right? We showed that f of x minus f of x naught is the same thing as the integral from x naught to x. That's going from here to here. Notice that the x minus x naught just became the coefficient. So it's just a numerator that turned into that. And then we use the intermediate value theorem to show that that value is the same as the height of the function at some point in between x and x naught, which we call c of x. So that's taking this and turning it into f at c of x. And then finally, since c of x is sandwiched between x and x naught, and since f is continuous, then as x approaches x naught, c of x approaches x naught, and so f of c of x approaches f of x naught. So that's what we got. We got the derivative with respect to x of this function is equal to f of x naught. Some value. That's it. It's a small proof, but there's a lot going on in there, which is one of the reasons I wanted you to read it ahead of time. Good? Do we need to take a bit of a break before we continue with the corollaries?
No. I think we're fine. I can leave for you guys to let's go.
Alright. Yep, we'll take a quick break. And then we'll continue with all the corollaries.